So I thought we'd go ahead and get started here. There's always some stragglers, but for an interest of time, both of Mike's time and all of you, I just wanted to thank you for coming down to the Integrated Design Lab. Once again, also thank Idaho Power, who continues to be a great sponsor of these programs and others here at the lab. And I'll do a really brief introduction to Mike. He's been involved in one way or another of energy modeling or energy analysis for a few years. There you go. So probably before some of you were born, but that speaks less to your age and more to their youth. If that makes you feel any better. He's worked with us as a collaborator at the lab on a number of projects over the years. He's a great resource for us and for professionals generally. So I would encourage you to ask him a lot of questions and then use him in the future as resource for those sticky problems that might come about. His company is Solarc Energy Group. I guess without further ado, I'll let him take it away. So thank you.
There we go. Does that better? All right. A couple of caveats. First of all, we're going to talk modeling. Now, modeling is a broad topic, and I know some of you have experience with it and experience with different software packages. Today, for better or worse, we're going to talk about DO2 and Equest. Why? Because when I started modeling in 1984, I started with DO2. I've been using it for 32 years. I know it intimately. But a lot of what we talk about, it has common ground with many whole building hour by hour energy simulation tools. And we're going to talk about a particular application that of extracting hourly custom data out of your model. So this would be a process where once you got your model up and running, you're defining custom reports, you're extracting data, whatever the data of interest would be and whatever your tool can allow you to extract. Equest just happens to have a very streamlined user interface where you can specify whatever of tens of thousands of variables you want, and it reads it right into a comma separated value Excel file and opens it up for you by pushing a few buttons. Who here has used Equest or is an Equest user? First of all, and how many of you, if any or all of you, have regularly used hourly report functions and features? A little bit? Okay. So what I've prepared here is a few slides just to give you some examples in these categories, and there's many other potential applications. This can be very informal. I'm totally good with that. So if you have questions, just interrupt me and we'll have a little discussion as we go along. I think we'll have a little time at the end when we wrap up to kind of open it up. So be thinking if you guys get some thoughts about, hey, I'd like to talk a little bit about this application that I use hourly reports for that's pretty good. I think we'll have some time to share some information amongst each other. Like these BSUG meetings should be a little bit of that we have an opportunity to share. So I'm going to talk a little bit about how I like to process the data, and then talk a little bit about applications and uses of this data once processed. So because it's the Integrated Design Lab, I'm going to show you some pictures of this is actually of a Boise project that it has never been built, may never be. But I'd like to title it Illustrating Integrated Energy Design. I use hourly reports almost extensively, maybe not exclusively, for our firm's internal quality control and quality assurance reviews. And I basically tell people, at least using Equest in our company, if you're not doing hourly reports and checking your models, then you're not meeting my minimum thresholds for job performance. I do not trust a model unless the modeler has gone through a reasonably robust process of extracting hourly data and cross-checking the input expectations in your model. And you can do it, and once you get some experience with it, it doesn't take very long to do it. It just is a kind of a modeling practice. It takes some effort to initiate that and institutionalize that in your modeling practice. Once you do it, it doesn't really take that much extra time in the overall course of the project. There's a whole bunch of other kinds, what I would characterize as more high-performance design support applications. And we'll just touch on a few. So I use hourly modeling a lot to just get in and extract weather data out of TMY files. Because you can do it in Equest with the building creation wizard. It takes about 1 minute to get the information out, and then you can process it in Excel to the extent of your Excel capabilities. How many pivot table users here? Any pivot tables in Excel? Super powerful feature. If you're going to be processing data that you're extracting with hourly reports, learn about pivot tables. They are incredibly powerful. So I'll show you some quick examples of that. We'll talk a little bit about weather data extraction and analysis. I'll show some examples. This is a nice little piece, the shading and facade optimization, a way to use hourly reports to interact with architects who may know nothing about hourly modeling, but know a lot about designing facades of buildings, windows, shading, etc. And so this is a great place for modelers to interact with architects as they're working on that facade to craft the loads in the perimeter zones to what they should be or could be to support high-performance design. So these two are, the load analysis and facade optimization are kind of merged in my examples. And then I do design of mechanical systems, and I do a lot of design support and design assistance using this tool. And almost inevitably, if I'm doing design assistance on a project, playing that role, and I'm using, I mean, I don't really even understand where I sit today how I would do it without hour-by-hour modeling and without using hourly data out of these models. And so I'll give you some examples, some solar designs, some passive design examples, but this can be very basic HVAC design assistance as well. When you open up your comma-separated value file, and if we want to have some time at the end and just step through an example very quickly for an Equest user, what the steps are, we'll do that. But this is what you get. You get this comma-separated value file with 8,760 rows of data if you just accept the default report, which is give me data for every hour in the year, every hour in your annual simulation. And the columns are as many as you want, whichever variables you request. And they all start with month, day, hour, and day type. And then the rest of that, where we start listing variables up here on column 9, those are the user-requested data, the user-requested variables. Literally, in a large model, you could have 50,000 variables available to you if you wanted to really dive into this. I don't think anyone uses it, but we did talk, for those of you who might be familiar with the research work, the Targeting 100 work, the University of Washington Integrated Design Lab, we talked about possibly building static databases with the energy models that were being used for those hospitals that would be populated potentially with billions of data points. So you could kind of do crafted simulation using a static database that was generated by hourly reports out of the energy models. I don't like to look at numbers for too long, and I'm an engineer. But if you're going to put up a table of numbers and then try to explain it to a group, good luck. It just doesn't really register for most folks. So the nice thing about Excel is you can draw pictures of the numbers, and they're not great pictures, but they're pretty good. And as you get better with the graphics capabilities of Excel, there's a lot of flexibility. So this is what we put together for a little project that was being considered here in Boise, the Discovery Center addition. And the idea here was to just kind of step through the early design phase energy modeling picture of the design strategies that the team had largely already developed, but wanted to have some confirmation and some addition with renewable energy system thinking. So what we have here is we have a picture of an entire year of loads. The blue is the cooling loads at the integrated building level The red is the heating load, so we're going negative, so the farther negative we go, the higher the heating load. And then the yellow is the hour-by-hour electric load. So just at a glance, here's your energy picture of an entire project. And then we're flagging the peaks and also paying attention to the area under the curve, the total annual energy use. And this is just out of the box, a generic orientation, the design as it, the massing and the appearance of the design as it looked. And then we've just stepped through a series of design strategy categories. And so the first one's just being a little smart. Oh, I got a duplicate here, I'm afraid. First one's just being a little smart about optimizing your orientation, looking at your facades, and picking the right design criteria. What's the difference between designing cooling loads at an interior design temperature of 72 versus 74 versus 75? It can be meaningful. So already we're dropping we're dropping about 9 tons of load, more than 10% of our peak load. You can see that the appearance between the area under the curve is shrinking. We're dropping our peaks on heating, and we're dropping both our peaks and our area under the curve for electricity as well. Not huge on electricity. The next move, and these are all layered on top of each other, which kind of the classic rolling baseline, if you're familiar with that term. But now we get a picture of the integrated design. So and one of the aspects of it is we want to craft loads, we want to reduce them, and we want to reduce overall energy use as well. So now we got a good shell. Again, cooling loads coming down, heating loads coming down, electric loads coming down. You can kind of see the difference here. And now we're focusing in now on internals, plugs and lights, not necessarily people, but a major effort on plugs and lights in this project. And this is a big move now. You can see we're really starting to see that our peak cooling load from our code baseline starting point is half of what it was. This is going to start making your mechanical engineers and your mechanical contractors very nervous, because you're now deviating dramatically from their experience and their rules of thumb. And so getting this out in front of people early on to set expectations builds the odds of success for a high-performance integrated design. Otherwise, if you wait till the end and say, hey, your loads are really 1,000 square feet per ton, not 500, guess what? They're not going to take the risk. You've got to be able to have that conversation as we go through. Actually, you'll see that the heating peaks went up a little bit. That does happen when we drop internal loads. But our electric load overall is dropping. And then finally, we get to what we framed here, alternative systems. And there was a number of different alternative systems here. Radiant floors were at a zone level. And some ground-coupled heat pumping and evaporative cooling, kind of strange hybrid concept combinations that fit Boise from a climate standpoint and fit in with the and you'll see that the cooling loads continue to drop. Why would that be? Think about conventional systems. This is a little loads piece that I always like to, between these two slides. Conventional HVAC systems impose loads on themselves. It's one of the reasons why certain codes, like the Washington State Energy Code now, is regulating the DOAS systems, and zone level heating and cooling is now a code requirement. They're getting rid of these integrated central systems that have inherent amounts of simultaneous heating and cooling. So you've got overcooling and reheat in VAV, you've got fan heat, you've got the ventilation load that's just coming in without any heat recovery on it. So a lot of loads, and in some projects, the loads that are being, on the cooling side, that are being imposed by the HVAC system on itself are greater than the overall loads that the building is imposing on the system. So be aware of that as you're having conversations, doing modeling on projects and having conversations with design teams. It's not just the architect who's responsible for crafting loads. The mechanical design team is also responsible for that, and the two working together are going to get you here, where you now start to see that we don't have red lines and blue lines stacked on top of each other anymore. We've managed simultaneous heating and cooling and we've almost eliminated electrical peaks entirely. And now we're at a place where this project can talk about its renewable energy systems and how to get to a zero energy performance level. So that is what I would characterize as illustrating integrated energy design, using energy models, using hourly reports, and using the power of Excel, which is an awesome, awesome tool. Okay? Enough on that. We're going to shift to kind of, and this is going to be a little more shotgun approach, a little discussion of some of the internal quality control and quality assurance uses that I've just imagined some that we use on a regular basis. And I'll be zooming in some cases here. So the time scale on this graph is the same as the previous graph, so we're showing every hour of the year. And this is a massaged, so we've extracted data on a modeled air handling unit, VAV system, and I've massaged the data inside Excel to graph the percent of peak design flow rather than just CFM. You'll see this as a common theme in some of my examples for the rest of our time together here, where I like to create a parameter with doing some calculations on the raw hourly data before I put it in graphical form and start analyzing it, so that for me it's more comparative. So this is a good example. What's the percent flow? Do we ever ramp up to full flow? You would be surprised if you start diving into your VAV models. This is a chronic problem in DO2. It's underestimating. It rarely ramps these VAV systems up to anything close to full flow. Now, arguably, you're rarely going to ramp up to full flow. But if you never ramp up above 50%, there's a problem in your model. You can see we get to about just barely over 70% for peak some of the days in the summertime. In the wintertime, we're hovering around 40 to 50%. And then I've just zoomed into my peak day to kind of look at it. And what I have here, time zoom, this is really a nice feature. We can go back to this model, pick the peak, zoom in on that peak cooling day. You can pick any day of the year, really, and zoom in and start looking at what it looks like. So the blue line here is the percent flow. So you can see we're actually off during an unoccupied period. That's good. And we're ramping up in the morning. I mean, this is a pretty logical flow. We are seeing a load reduction at noon. So that, by implication, I would say somehow the modeler has plugged in some people leaving, some lights turning off, some other things happening in the zones. Maybe that's appropriate. Maybe it's not appropriate. We peak in the afternoon and then we drop. So it doesn't, the blue line doesn't bother me too much. Now the red line is the predicted discharge air temperature in a model. This one, if you don't pay special attention to it, you're probably not modeling what you intend every time out, because there's a throttling range in Equest of 4 degrees, which means if you're dialing in a 55-degree set point, if it needs to be 51, it will be, even if the design will never achieve 51. You'll see where we're at. We're running at 51 and 52 constantly in this model on a peak day. Probably a mistake, probably needs to be corrected. So looking at the modeled discharge air temperatures in conventional HVAC system models, critical thing to look at. Without looking at it in hourly reports in Equest and DO2, you probably have about a 25% probability of it being correct, if that. And these two work together, by the way. If this was up at 57, our airflow would be higher for the same load. So here's some interesting little graphs where I'm starting to do some different stuff inside of Excel that I find interesting. So using the XY plots feature in Excel, not just graphing out on a line graph on a time series, but actually having one independent variable. In this case, I've requested an hourly report where I'm wanting the discharge air temperature and the outside air temperature, and I'm plotting discharge air temperature as a function of outside air temperature. Because I'm now able to kind of say, look at the discharge air temperature controls that are as they're being modeled, and compare them to the discussion of what the control sequence is supposed to be. And in this case, you can see that we have reset going on. We're resetting between about about 52, 51 it drops down to at the hottest hours, and 60. But you'll see there are some hours in cold weather where we're not up at 60, we're dropping down as low as 55. So there's some things to look into here. This is actually a reset sequence where we're trying to simulate a zone responsive reset, polling of the VAV terminal units for those of you who are HVAC folks here. So it's not a direct outside air reset, but it tracks outside air temperature pretty well. So the first thing I'd want to see on reviewing controls inputs is, are we doing, if reset's intended, is the model resetting? Is the model resetting between the minimum and maximums? And does it make sense on a seasonal basis where you can imply magnitude of heating and cooling loads, that it's mainly doing what it's supposed to do? I would conclude here that I feel reasonably confident that this reset's defendable. I'm a little concerned about these low temperatures here. It's probably a mixed air issue. So I might investigate my outside air damper controls and my minimum ventilation inputs. And I might investigate my throttling range and saying, how come the model is dropping down to 51 on the hottest hours? I don't necessarily want it to do that. And this XY scatter plot, if you haven't used that in Excel, it's super powerful. I'm going to show you a few other graphs as well. So this is another one where I've plotted the fraction of outside air against outside air temperature to check the economizer control sequence. So the first thing I'm seeing is that I'm at 100% outside air between about 60 and 75, and then I drop back down to minimum, and my minimum is running right about 13%. So right away, that's what is in the model right away. You should be able to cross-check that. Is 13% minimum what the engineer's been talking about or what we've been talking about in the project? Do I have an economizer high limit set point that drops back out of economizer at 75? Is that the right point? And then you can kind of see that as with this nice little interesting curve, as we drop down in cold weather, that actually we never get down to minimum. So we're always staying in economizer. The only time we drop out of economizer is in warm weather. And that's pretty typical for the Pacific Northwest, unless you have a purposeful active economizer low limit to drop out of economizer in cold weather. That's usually done if you have a heat recovery chiller or some other device where you want to add cooling load in cold weather and meet that with a heat recovery device. So I would conclude here for what, in my mind, what I was intending with an economizer control, that this outside air damper control in terms of airside economizer cooling is a pretty good representation of the control sequence. But these control sequences, in Equest, you can make some input changes, but again, there's no easy pre-formatted output report that you can look at that's going to tell you, yeah, economizer's working. You got to, if you want to know it, you got to go and create your own custom report. Here's an interesting one. In this case, I'm plotting so I'm massaging the data. I've requested information about the supply fan motor KW for every hour, and I've requested information about the supply CFM for every hour. And when I'm plotting, and then I'm doing calculations so that I can look at the fraction of peak power as a function of the fraction of peak airflow. This is a fan power curve. So I'm now deriving the flow fan power relationship that is embedded in this model, and I can compare it to what, as a modeler, I would expect and believe is defendable. So in this case, you'll see that we're running at about 10% of motor speed for a lot of hours down here in low flow conditions. And we're rarely ramping up above 40%. We're never above 70. We're rarely ramping up above 70%. We're never above 40% of fan power. I would question this model. I would immediately think I'm not estimating appropriate amounts of fan power in this model. It's underestimating. If you're underestimating fan power, then all your fan efficiency measures that you're playing with, like we're going from VAV to a radiant heating system, you're underestimating the fan savings associated with that as well. My last example of model QC and QA, and some of you should think of some issues that you've wrestled with, because I know a few of you have. This is one, at least in DOE 2, that's always a tough one. How much air infiltration is actually moving through a zone? So you plug in a rate, a peak rate, in one unit or another, CFM per square foot or air changes per hour. You potentially link it in Energy Plus. You can't unlink it as far as I can see from wind data in the weather file. So there's a external calculation link to the wind data in your weather file in many runs. And then you link it to a schedule as well that modifies that peak. So understanding how much total CFM, or in this case CFM per square foot of floor area, is actually moving through your zone and moving through your building, there's no easy report to find that. That can be a meaningful number. Check out, if you just check out your fan operating hours on a lot of models right out of the box, what you'll find is that the fan is cycling on an excessive number of hours at night. Something's driving the temperature in the wintertime down below the night set point, or in the summertime up above it. Typically it's too much infiltration moving through your zones at night. You've got to check it. You've got to verify it. I mean, you can do it in a kind of a crude way by extra review of your inputs, but ultimately this is a much faster and more effective way, because this is what the models actually do. So I'm just interested if anyone else has any model QA, QC issues that I don't have to come up with any now. Loads is one I know that Skylar and I have wrestled with independently on the same project. But maybe we'll talk about that at the end. Climate analysis, I know you guys do this at the lab, and the labs have been doing it forever. I don't know how many other modelers are asked to support teams kind of early on with providing some climate information. But even if you're not, there are other uses for those TMY3 hourly weather data files. You know, a lot of times we're not necessarily doing complex hourly models, but we do a lot of temperature bin calcs inside of Excel. So I'd like to get the weather data out of a TMY3 file and into a temperature bin table for whatever location I'm working on. And you can use the hourly report features of Equest to do that in about a minute. This is just a simple graph of every hour of the year of Boise out of the TMY3 file, dry bulb temperature. It's kind of illustrative to know what's in your TMY3 file for Boise. You never, -3 degrees is the lowest temp. What is about 102 is the hottest. So you guys kind of know Boise's weather. Is that reasonable? It's not. It's probably pretty reasonable, but you can kind of see your coldest week is happening in January. December and November never really get too cold, about 20. Here's an interesting little XY graph, and I use this a lot when I'm doing simple non-simulation efforts like temperature bin calculations, and I want to know the wet bulb. Say I'm trying to calculate a chiller plant condenser water reset scheme where I want to do a wet bulb reset. So in a temperature bin, it's helpful to be able to have a little relationship where I can make an approximation, an estimate of the average wet bulb temperature as a function of dry bulb temperature. Plotting wet bulb temperature on the y-axis, dry bulb on the x-axis, and developing a scatter plot will allow you to do that. If some of you haven't used scatter plots, I don't know, if you haven't used scatter plots, then you probably haven't used the trend line feature built into the scatter plots. So this is a graphical regression feature built into Excel. So you can curve fit a number of different curve forms and show the equation of that curve as an output on your graph. And now all of a sudden you've got a nice little regression equation that you can plug into a simpler calculation to do pretty sophisticated stuff. And it all starts deriving from extracting the hourly data and processing it. Yeah.
So does Equest have wet bulb?
The TMY3 file has wet bulb temperatures in it, yes. It also has dew point. This is a picture in Excel of the top half of the Boise bin table. And this is what I would get by doing a pivot table on the data And in this case, putting the hours of the day across the columns and the outside air temperature across the rows. And then you can change the field settings to like 10 different settings. They'll sum, they'll average. In this case, we just want to count how many occurrences of that 101 degree temperature are happening in the weather file and in what hour of the day are they occurring. So it's just a count. The total sum of all the numbers in a bin table adds up to 8,760. But you can separate it. You can process it by month. You can process it by day. In pivot tables, you've got a lot of flexibility about how you process the data. And a lot of simple model, a lot of simple energy engineering. It's not so simple, but non-simulated energy engineering calcs are now being done more and more with bin temperature calculations. This is a summary of just the average solar radiation combination of direct and diffuse out of the TMY3 file for Boise. And processed, averaged over the month and processed in the units or BTUs per hour per square foot. So if you're being asked to analyze some solar systems, either how do we manage excessive solar loads in the summer, or should we design solar thermal systems? What's a solar electric system going to look like? I mean, it starts with raw data. Is Boise a good solar resource location? You probably all kind of know that intuitively, but you may want to compare it to other locations. Many locations around the planet have this data already processed for them. So you could get that data, say, for Albuquerque, pull it out, compare Boise to it, and go, hey, we're pretty good. We're pretty close to, you know, what you would consider prime solar locations. Maybe a little off in the winter, maybe a little more in the summer. Still pretty good. So those are some examples of climate analysis. There's a lot you can do. I mean, shading calendars, cloud cover, a lot of the stuff that the labs do. It's all really available to you if you wanted to dive into using hourly reports and extracting data out of these weather files. I'm going to talk a little bit now about a little bit more sophisticated use of hourly reports where we're really supporting design teams to help them optimize their design. And we're doing it using forms of data and reporting that are not, that you have to create. They don't exist in a pre-formatted format. You can't get a report out of DO2 or Equest that's going to show an architect. This is a picture of a south zone, a little box, but a big one, lots of windows, about 35–40% glass in the south zone. No shading. What are the zone loads for the entire year? And you'll see that 0 is here, so we have negative loads, which means there are hours where this zone is calling for heat. But most of the time, this zone is calling for cool. I like to draw a line, right? This is, and I've processed this. This is BTUs per hour per square foot of floor area. So it's indexed. It's an indexed load. Now we can compare this zone to a small zone, to another building, and we can start talking about rules of thumb. I like to just draw a line here saying a good rule of thumb for high-performance design, get your peak load, cooling load down below 20 BTUs per hour per square foot. Once you get down there, you can start doing radiant floors and a lot of other solutions. You can't get it down there, you're going to be limited on the different alternative load management solutions that are available. So this is just a code out of the box building, nothing special, no great glass, no shading whatsoever. You can clearly see the south zone. Anyone surprised that our peak is happening here and not here? Sun angle and reflection off the glass. This is a solar-driven load dynamic, and in the high sun angle months, we have less transmitted solar load through that window, even in an unshaded condition, than we do in the lower sun angle, but still warm afternoons. This is a pretty classic Pacific Northwest South Zone load profile out of the box. It shocks some people. Most engineers are doing their load calcs on June 21. And if you did a June 21 design day in Equest, it would not be the peak day because the solar load would be way less than mid-September to mid-October.
How was your fixed shading operated in October?
Yeah, well, in this case, we have no fixed shading. So this is kind of how then I start adding things. So Same model, but just stick an 18-inch deep overhang at the head of the window. There to there, there to there. Big difference. Now you can clearly see, hey, in the summertime we're down below, but we still have this problem in low sun angle conditions, as you would expect. Now let's deepen that. 3 feet. It's going to start getting a little dicey for some architects at 36 inches, but you can see it makes a big difference. Now when's our peak? It's in December. But for more or less, we're starting to get into the ballpark across the year. I'm less worried about December because I'll just open some windows or turn on the airside economizer and meet that load, if I have airside economizer. But I'm starting to get down there where I'm opening up the design flexibility for the system's design. Now I just layer on good glass, best in class double pane glass with my 36-inch overhang, and I've got it. I've met my threshold. You can step your architect through this sequence of design strategies. I've even done it in real time, just sitting down in a work session and say, well, what's an acceptable overhang? Can we do fins? What kind of glass specs are you guys open to? And just start showing them, as long as you have a load threshold, a performance target that you're trying to shoot for. This is a really powerful work session, real-time modeling work session, where you have to do hourly reports because otherwise there's nothing that you can really put in front of folks that would mean something. But this does mean something. Yeah.
At this point, how much work have you done to really evaluate the internal loads of the building?
Not much. I'm focusing on a study zone at this point, so I'm trying to get those internal loads reasonable for that study zone. I don't want them to be unreasonable. I want them to be, the schedules to be reasonable for the anticipated use. And I want that zone to reflect, at least the facade on that zone to reflect what the architect's early thinking is. But I'm not worried about the rest of the model, so I can just do a simple shoebox model with a little focus on one zone and just drill into that zone and study it. Now, once we get that zone, if I want to study an east or a west facade, I just rotate the building 90 degrees and rerun through the process, which you'll come up with, obviously, with different answers in the northwest, on east, and west. So now I'm going to zoom in just on that little box and say, okay, we've got this weird end of September peak. What does that look like? That's what it looks like if you drill in. So the red is the total zone load, and the blue is the solar load contribution. Kind of weird when you run solar loads in Equest. Why do we have a solar load when the sun's not out? DO2 and Equest out of the box is going to model a thermal lag associated with the mass of the construction components that are in your model. So this 3 a.m. solar load is a carryover with the math that's built into DO2. It's a thermal lag. It's a carryover from the previous evening and afternoon. Some of that solar load got embedded in the masses and is being pulled back out of the mass by the calculations several hours later. You can still see, even with our shading, this is our 3-foot shade, we still have a significant contribution from the sun in late September to the total load. I mean, the total load's about 18, and of that, almost 6, almost a third of it is solar load. Perimeter zone issues, east, west, and south, are always about the sun, always, unless there's no windows. So it makes it relevant for the architect to manage the sun. Here's another little graph that you can pull. Now I'm zooming into the window, and I'm saying, I want to extract hourly data on that day about, and in this case, one of the variables I can extract is the fraction of the window area shaded by that overhang. And I've actually got the 2 overhang conditions here, the 18-inch deep and the 36-inch deep. And you can see on September 28, in that sun angle condition there, that we don't cover all the windows. There's the lower 40% of the glass is not covered, which immediately explains the previous graph, but starts making me think, what's happening? So I just graphed that same variable over the entire year on that specific window, and there's your picture of overhang shading performance. So it does a great job, from mid-April through just about the last week of September, but it's starting to not do such a good job in the low sun angle conditions. And maybe that's fine. but in some cases that's not going to be fine. Skylar and I have our project. There are some projects where, especially if there's no mechanical cooling being done, you have to manage the sun even in October and November, maybe even more so in those. Typical fixed shading solutions are very difficult to do that, so it pushes you into the conversation that's tough in the US about dynamic external shading or electrochromics, but mostly it's dynamic external shading, and that solves the problem. Okay, so now I'm going to just wrap up here with a couple of examples of more direct and more, what I would call more sophisticated design support. And these are designs that, one is just a generic example. This is an actual design I'm doing. So when I get involved in doing designs now, I always have an energy model. This is a potentially off-the-grid house, but it's a grid interactive electric system. So the first thing we're doing, and it's an all-electric house, modular house, but we have to have a thermal model because the heating load, the heating energy end use is the most significant end use, even though it's a heat pump. And so the thermal model translates to an electric load model, and you can see the two lines here. These are our average kilowatt hours per day over the course of a month. So inside the hourly reports, I've massaged this significantly to get it down to something where the architect and the owner can actually look at this graph and go, okay, I get it. This has double pane, this has wait a minute. This is double pane, this is triple pane. So big question. If we upgrade to triple pane glass, does that materially benefit us? And by that, the definition was, can we buy significantly less PV and achieve our energy goals? And the answer in this case was, it is a benefit, but it's not going to really change your PV investment. So this was one way to help them dial in on the degree of glazing spec that they needed. And then what's layered on top of this these load curves are PV output curves. And this is something that actually Equest can do. I don't know if any of you have dived into that PV input aspect of Equest. It's simplified. It says, you know, there are many other tools out there as well. PV Watts Online will do it. If you use Solar Pathfinder software, that actually does a little bit better job because you can handle shading. This Equest does not simulate shaded PV surfaces. PV Watts does not simulate shaded PV surfaces, so they're idealized curves. But at this point, then we can kind of see where are we going to need supplemental energy, where do we have excess energy, how big of a PV system do we need, if it's off the grid, how much battery power do we need. If we want to drill into the actual hour-by-hour reports, here's a less processed report, and I'm just showing little snippets of the year to these guys. So this is, the blue line is electricity used in the first 3 days of August, and the red line for the system size that we've kind of landed on is electricity generated. So you can see in August that for this size we're generating way more power than we need, but the system size not for the summertime balance, but rather for a shoulder season balance. So we're going to be deficient. This is Seattle area. So we're going to be deficient in our overcast sky conditions. We're going to be exporting, or we're going to be wasting in our clear sky conditions. And then I just generated a little example of passive design. This is probably more applicable in the residential sphere than in the commercial sphere. But if you were working on a project that wanted to do passive solar heating, and it does occasionally happen in the commercial sphere as well, these are two profiles on, and this happens to be a sunny Boise day in the weather file for that same little simplified model. So what I've shown here is the solar load graph over a sunny winter day and the total load graph over the sunny winter day. And then I've added up the area under the curve. The two are interacting. So the reason why this guy is going so high is because of all this solar gain. The reason why it's not going lower is because there's some little thermal lag solar gain, but this is all heat loss through the shell and via infiltration. The area under the curve, it just so happens, represents about a perfect thermal balance on this day. Our total solar load is about 240,000 BTUs. Our total load is 25,000. It's almost balanced out completely. It's actually got a little more solar load than we need to meet the heating load, in theory, of the zone, assuming that we have perfect thermal mass to store the energy when we have it and to re-radiate it out and release it when we need it. And that's what this little graph represents. So this is the total load profile, and we're trying to capture this energy in a storage mechanism and use it when we need it in the other periods of the day. And now you can start getting in with some calculations in Excel to help your architects out. Damon and I were talking about this. There's just seems to be a real lack of knowledge about passive system design, thermal mass, all of this kind of information. And hourly modeling can really help illuminate. So in this case, I'm just very simple back of the napkin calcs. You know, if we're going to store 220,000 BTUs with the current load profile on a cold winter day, that's about what we would need to do. In the size of this, if we were trying to do it in a concrete slab and with the size of this zone, we would be able to store effectively in a 6-inch deep slab if we can raise the temperature 5 degrees, about a little less, about 40% of that. So we either don't have enough mass or our loads are too high. And so this could be a starting point to a conversation where the design team would begin to say, how do we get more mass in here, or how do we get these loads down? So that if what we want to use is the mass floor, then we got to get this down to where we have about 90,000 BTUs that we're trying to store, and we have about 90,000 BTUs that we need at night and during heating. And that's what I have for you today. And so I think we have some time. I can certainly step through, if it would be helpful to folks, either online or here, to show in Equest how you generate this stuff. Or if you have questions about anything you've seen, we can just have some conversation. Or if you have some ideas of ways you guys have used hourly reports on your projects, feel free to share them. And don't all speak up at once.
I think some examples would be fun to go through.
Okay.
Some of your favorites.
Well, one of the things that I would do, I mean, you've seen some examples that are processed for this presentation, but one of the things I would do is just that I like to do for people who haven't done a lot of hourly report extraction in Equest is just to show you, in theory, how quickly you could go from no model to, let's just use a simple case where, hey, I need the Boise weather data out of the weather file. I don't have it. I want it into an Excel file so I can play with it. Rishma? Yeah. Okay.
Can Equest just run on a design fix that you don't need to do an analysis on all 8,760 hours when you're just focusing on peak loads?
The answer is no. In Equest and probably most hourly simulation models, you have to define a simulation period. In Equest, if you wanted to, and it will reference a weather file, which may or may not have design day conditions embedded in it. The file has the data in it that it has in it. We're using that. So you're going to have to reference a weather file, and you're going to have to specify a simulation period of at least 1 hour. So, and that's probably not your design day. In addition to that, and we would typically just rely on the default simulation period, which is the entire year. In addition to that, you can specify a design day, but to extract hourly data, I do not know of a way in Equest to get the design day hourly data out in the way I'm going to demonstrate right now. And you have to be careful when you specify a design day in Equest. I have seen engineers get into trouble by specifying design days that don't align with some of the graphs we just saw. In the Pacific Northwest, if you specify the summer solstice as your design day, depending on how you're modeling your glass, you will have wildly inaccurate peak solar loads on that design day, because your peak solar conditions are going to occur somewhere between the end of July and the middle of September, typically. So now you can specify a design day in Equest where you're setting, you can set whatever date you want. So if you wanted to say, I want ASHRAE design outside air temperatures, and I want to overlay that with sun angle conditions from the middle of August, now you're probably getting into the ballpark and you of the appropriate cooling design day, and you have a lot of pre-formatted reports that you can access that are usable. But I don't know of a way to get hourly reports. And I would say that in my experience, I'm not so concerned about the extra data. It may seem a little daunting at first, but once you get used to working in Excel, it's pretty quick. It's not a time-consuming undertaking. So I just always default to a full year's worth of data for any hourly reporting. So let me demonstrate why it's not that daunting. So let's just open up, let's just start with an Equest example, starting from scratch. By the way, for you users who have not used Equest extensively, I'm going to be using the little feature in Equest called the Building Creation Wizard in this example. It's an awesome, it's one of the most powerful things that has been developed for the building sim world in the last 15 years. It lets you get a model, simple model, up and running in the next few seconds. So I'm just going to create a new project. I'm not going to spend a lot of time talking about the Building Creation Wizard, but I'm going to click this little button about Design Development Wizard. I'm going to just go ahead and live with all this. Now the entire model is populated with informed default values. In this case, for an office building, I don't really care what the building is. I'm just trying to extract Boise weather data. So the piece that I have to edit is this next little piece on this first screen to tell the program where the location of the project is. So I'm going to user select, and I'm going to go to the location on your hard drive in your Explorer where all the TMY3 files are, and you guys probably keep them in all different locations. But here's all the TMY3 files for the United States in this particular folder, and they're all organized by state abbreviation. So let's go down to Idaho. And here's what we have for Idaho, in case you didn't know. We got Boise, Burley, Caldwell, Coeur d'Alene, Haley, Idaho Falls. There's another Magic Valley, Jocelyn Field, I'm not sure where that is. Lewiston, Mound City, Mountain Home, Pocatello, and maybe one more down below Pocatello. But we're going to go do Boise. Might as well. It's the airport data, by the way. And that's it. That's all I need to specify. So I'm going to go ahead and click on the Finish button, and it's going to generate an Equest model. Now, for those of you who have used the Building Creation Wizard before, you probably know there's two modes of editing in Equest. And I'm pulled down the little pull-down menu at the top. When you get out of a wizard session, your default is wizard data edit. So all the detailed data that's in your model is not editable until you change the mode, which I'm going to do now because you cannot create hourly reports in the Building Creation Wizard. This is a detailed editing exercise. So now we have a model, and I have now made it available so I can edit that model. And where, I'm getting cut off here a little bit. Where you create your hourly reports is under this Project and Site Editing button. And if you click on that, you'll see right at the top of the list of all the elements that are in your model is the Simulation Output folder. And you have hourly report blocks and hourly reports as subfolders under there. We're going to add some report blocks. Creating report blocks is where you select your variables. And you'll see if I open that up, the wizard actually created two report blocks that it uses in some of its pre-formatted reporting. We're going to add a new report block. So I'm going to right mouse click and create another report block. And I'm just going to call this outside air temperature block. And I'm going to copy another block just because it's easier for me to edit that way. And here's all the categories of variables that are available in DO2 models when you create hourly reports. Weather data is under global, but you can I'll take a look at a few of these so you can get a sense of what's in here. But let's start with the global. And as soon as I'll go ahead and click on done so we can see what that looks like. No, I want to. You can see here's all of the variables that you can extract from the weather file. Wet bulb, dry bulb, ground temp, cloud amount, wind direction, absolute humidity ratio, solar radiation, wind speed. I mean, you want to do climate analysis, this is one way to do it. It's not the only way. It's not the only data source. In this case, I'm just going to specify outside air temperature as the, and I always double check that I got it, that it actually took. And so I'm going to extract outside air temperature for, and the default schedule is for every hour of the year. And so then you have to go to your hourly report folder immediately above and select the new block that you just created. I'm going to disconnect these two blocks that were already in there because I don't want my Excel file to be burdened with excess data. So you can have a whole bunch of variable specifications, if you will, but you don't use them unless you ask for the report to be generated. And that's what we've just done here. I'll save it. I'll run it. Because it's a very simple model, it takes about 2 seconds to run. And then I will click this little button that says View Detailed Simulation Report. It's the only pre-formatted report I ever look at. And when I open it up, Equest users and DO2 users should be familiar with this little guy. And there's 1,000 pages of other pre-formatted reports in here as well. But you may not be familiar with this little button over here on the upper right-hand corner that says Hourly Results. So that's the button you click on to get your hourly reports out in electronic format. And as soon as you do that, it creates a comma-separated value file, and all your data's there. Now, you guys want to see a pivot table? Okay. So the first thing I do is I just, because all the variable names are at the top here, in this case outside air dry bulb temperature, I just wrap those. How come I can't see? Let's just. And then I just develop a technique where I'm going to say, I leave all the raw data over here. In any calculations or massaging I do, I either create a new tab and do it, or I do it over on the side, so that I don't edit the actual data that I just requested. That just stays there. So when I'm doing a, let's do this. When I'm doing a pivot table, I do the same thing. I'll just bring the data over to a another part of the, dry bulb temperature. And then I'll do my pivot table on that. So I just copy it over. So the month, the day, I'll just show you a little bit of simple stuff in pivot tables that's kind of fun. So let's just say you wanted to create one of those temperature bin tables for Boise weather, because you were going to do some bin calcs in Excel. So I just copy it down to get all of them in. Sorry. Okay, and then pivot tables are under the Insert tab in Excel, and then Pivot Table, and then I just click on Pivot Table, and it's going to take, the default is to open it up in a new worksheet, and so I open it up in a new worksheet, and you'll see over on the right-hand side, there's the labels of all the columns that I just inserted into this pivot table. If you haven't used pivot tables before, it'll take you a little while, but I like to put the hours across the top, the dry bulb temperatures along the rows. You can put filters in, so I'll put the month and the day as report filters, and then I'll put the dry bulb table in as for the values, and it's defaulted to the sum, and so I just you can right mouse click anywhere on the table and change the field settings, and here's all the math or arithmetic processing you can do in a pivot table, but for bin tables it's just the count, and so there's your bin table basically. If you want to go, it's set up from the coldest hour, the coldest temperature in the weather file, to the hottest, but you can sort that and reverse it from largest to smallest. This is what ends up being what. And then right now, this is for all months and all days, but if we wanted to just say, well, I want the bin table just for January. So you can pull that down, and you can just select January only, and now there's your bin table for January, which unfortunately is cut off here, but it now starts at 53 degrees down to cold. And so if you were working, say, on a elementary school that was not where you really only wanted to look at the school year, you could easily do that and just create a bin table just for the 9 months of the school year. So that is about, now if I was sitting down to do this at my desk, I would have done it about 20% of that time. It does take a little practice. So if you haven't used hourly reports before and this is intriguing to you at all, or you've used them relatively little, you're going to have to find a way to start using them and get used to the process. Part of it's just which mouse buttons do you click, and part of it's starting to become aware of what you can do once you get this data in Excel and what's available in the software tool that you're using. Energy Plus can do hourly reports, DO2 can. I can't speak for the other modeling tools because those are the only two that I use.
Do you have any tips for kind of automating the process as you go through different simulations, sending the data automatically to spreadsheets, or do you use tracking?
I don't do that, so I can't. There's probably people here who might be able to give you tips. I like to drive the bus with like a stick shift, and I'm old school. So I just figure out after a while how to make it happen fast enough for me.
Yeah, you can have a macro where you just drag it all, and you drag in your export into one folder, and it will automatically populate, this way.
I will show you. Yeah. So here's the old school tip. If let's see if I can open up some of these if I've got them here. So like here's my folder for, if I go all the way to the top, here's the raw data and with some data processing for some of those shading graphs. Once I get one of these built up with the graph that I like, with the chart that I like, then I just save it as a unique name, and then when I run the next hourly report, which is exactly the same variables, I can just copy that chunk of raw data, paste it right in here, and it immediately draws a new graph because it's all linked. That's my little tip, but it's not a macro.
Yeah,
I'm still driving it. It would, yeah. For those of you who are the next level of Excel capable beyond me. But that's once you get the data. I don't know of a way to automate the process internal to your simulation tool of choice about which variables you want, because it's totally project dependent and project team dependent. You're not going to want to look at the same things every project out. Now, you may want to develop some QC checks for typical simulation problems, like when we're doing a VAV system, we do these 5 variables. But like we were talking about, shading might be really important on one project and not even an issue on the next project. So you kind of got to take your cue from what I'm always asking myself, what design questions can I answer for the design team using this tool? It's taking the usability of simulation into a level that I think makes it viable, really uses the power of simulation, and doesn't just say, well, if we're doing a lead project, we'll model, otherwise we won't. That's about the least valuable use of a model, in my opinion, is to actually say how much energy is being used. What we really should be doing is diving in and answering all these questions using the 10 to 1,000 to 100,000 other little answers that this model has created that we never look at unless we dive in and look at it. And sometimes sometimes you have to hold the hand of the design team. I'll usually ask them right up front, what are your design questions? If you could ask this model any question that's out there, what would you ask? And half the time there's no response. So then I start queuing it up. Well, are you interested in solar load? Are you interested in how much glass is too much? What type of glass makes the most sense? Are we interested in sharing with the contractor or the engineer what their peak loads are? I don't want a chiller that's twice as big as it needs to be. Those kinds of things. And then it makes, at least for me, I've gotten to the place where this is an indispensable tool for every project out the door. I was just talking with a few of you before. I've seen a dramatic reduction since the early part of the century in the number of projects that formally integrate energy modeling. And I was expecting it to go the other way. I was expecting that as we had more and more folks who became used to their tool of choice, that it would just become an indispensable part of a project design. But I think the value proposition of modeling is still not well understood by most design teams and most clients. And it's part of my mission is to help show some additional value that's not traditionally talked about. I think we can leave it at that unless you have other questions or comments. You're welcome.